1, 2, 3.
1, 2, 3.
Okay, dear ladies and gentlemen, we are continuing our stream marathon. And okay, today is the article about experiments, again in tungsten disulfide. So I was preparing this article for 2 days, and I should say that this article is one of the hardest for me because this experimental technique is new for me. But I did my best, understood it as much as I could, so I don't have much to tell you before, and the stream will be most likely a very long one because there are a lot of details in this article, but okay, I hope that I will finish it in 3 hours. So that's why let's just jump to the discussion of article to save at least some time, because I really don't want to spend 4 or even 5 hours on this very little but very informative article. So this article is crystallization of polarons through charge and spin ordering transition. Again, tungsten disulfide. We have seen a lot of streams about this material, and still there are so many things that I haven't yet discussed. So that's a relatively new article. Only 3 years have passed, actually even less than 3 years. And okay, it's relatively cited article. So it has 21 citations. So sometimes typical experimental articles get even less citations. So someone knows this article, some people know this article in the community of tungsten sulfide. And okay, in scope of the first overview, let's just scroll through it. It has, as far as I remember, 7 pages. Of course, we don't count pages for cited papers. But these 7 pages, they are very dense and they have really advanced ideas. That's why I am assured that the stream will be a long one and very complicated one. And you see, like, okay, for me right now, these plots are relatively not complicated. Still, it's a very big and complicated job to get these results. So the technique that is used is really advanced, and the data analysis is also very profound. That's why I think that there is a big value of this article because it's very hard to get these results. But how to use this article and what can we do next after getting such results, that's not the thing that I'm assured in, and I have some guesses, so we'll discuss them later, maybe in 5 minutes. I just wanted to show you the original article. And now let's open FST, and that's this article in my app. So let's start from the beginning, from the general overview. So we will see a lot of times these plots. That's why I have opened them here in this special window, because we are going to return to them, I don't know, maybe 100 times during the stream. Basically, all the article is a collection of comments and conclusions from these plots and comments about how they were obtained. So the main idea of the article is that, main conclusion that is obtained is that with this technique, which is called pair distribution function, authors analyze positions of atoms. So as far as I understand, nothing is about electrons here. Okay, but let me write this question. Uh, and yeah, like I'm not expert in pair distribution function. That's actually the first article ever I have encountered this method. So to some extent I understand it, and I have also prepared for you the takeaway. I mean, maybe some key formulas, but it should work. Okay, it's not that easy to make this app work because few people were developing this. But okay. So where are the formulas? They are somewhere here. So in order to understand this article, it's really good to learn some or revise some basics of pair distribution function. And it will take maybe extra 10 minutes, but I think maybe it's worth it. So we will come to this theory maybe after I tell the main results and the main conclusion, and it will be a good introduction. Then we will go through the article itself. So they use this special method, pair distribution function, to get all the information about atom positions of atoms. This information is not only in one layer, but also between layers. I mean, it takes into account distances between layers. I'm still surprised how that it's possible that it works like this, because I can imagine diffraction and scattering of light on one layer, but if you have like interlayer distance, then that's already goes beyond my imagination. But that's a really advanced experimental method, and one needs to like think at least a week about it in order to understand it. And of course I wasn't doing this because the idea was to get as much useful as I can from just this article. And the basic understanding of pair distribution function, or PDF, which will be discussed throughout this article, is that we shine light on the material, it has some diffraction, then we get some interference pattern because somehow we collect these rays of light after passing the lattice of the material. And then after getting intensity of the light, we do some averaging, we get some do some transformations, and okay, there are big ideas behind these transformations, and the sketch of them is shown here. Like from intensity, we get the object which is called big S, then an object which is called big F, and then we have finally the thing that is assumed by pair distribution function. So this is the line of the transformation that is done in scope of data analysis, and we are left with the final result. The wavy curve that describes the correlations between distances in the material. So what is really surprising and really manifests a very deep level of understanding of materials is that this curve actually is not chaotic. It's not some noise. It's something that can be driven from theory if you know all the parameters of the lattice. And here, for example, we will see later that there is a fit. So this red line is the prediction of theory, and the green line is something that we get from experiments. I still don't understand how it's possible to do such an exact prediction. I mean, of course, there are a lot of parameters that are fitted, but still, when I think about it, it makes me feel that that's such advanced and like very sophisticated method. But people who know pair distribution functions, then maybe they are working several years with this, so maybe it's not a surprise for them. But since it's the first my article about PDF, I'm still surprised how precise we can do predictions. So the essence of the article is that we shine the light, we get this very curve that looks like a noise, but it's actually not a noise at all. And out of this curve, we drive a lot of conclusions, actually all the conclusions about the material, about the positions of atoms. So you might think, like, how is it possible to get such a lot of information just from diffraction? And in order to understand it, there is this whole 7-page article which explains everything, and that's what we're going to discuss during the stream, which conclusions we can get and how we can use it. And the last part of the announcement of the results is that the main takeaway from this article is that there is this material, of course, and there are different phases, and if we decrease temperatures, the phases change. So you can open the TMDC. Sorry, it's not focus structure, but I have not opened that article before in the focus structure, so I need to use just the PDF. So we already know that that's the typical phase diagram. So this tungsten disulfide has a lot of phases: metallic, nearly commensurate, fully commensurate phase, so on. So that's already well known. And if we use PDF, then we'll also see that this function changes if we go from one phase to another, and the transition happens if we decrease temperature. And we can decrease also pressure, but they're not discussing pressure. I assume that if we decrease pressure, the results of the experiment will be the same. So it changes, and that's not a surprise, but still we can get a lot of information of how exactly the modulation of lattice changes. And spoiler, not here, that's here, the collection of 4 figures. So here, after maybe 1 hour, we will see how all the positions are changed, and we will discuss this. So there are a lot of parameters, the distances, for example, the angles, and there are a lot of atoms, so there are several distances. So all of this can be driven from this experimental data about correlations, and that's one thing that they do. Another thing that they discuss the existence of polarons, and the main idea is that we not only have a new modulation, which is already known before, but we also have some local deformations. And in these local deformations, maybe they were obtained first time ever in this paper. I didn't check, of course, other papers, but during reading, I felt that that was the main discovery here. And we can't explain these local deformations from charge density wave theory. So we are left with a strong argument that polaronic theory is the most precise theory for this material. However, of course, maybe it's not known, or it's hard to tell how exactly to use polaronic theory to predict the local deformations that are deduced from this data. But that's another big discussion, so that goes way beyond this experimental article. and I don't have a clear answer because, okay, we will still discuss for a very long time this article. Okay, so that's the main idea, that they use this method. They get a lot of data for a lot of temperatures, and they have a lot of parameters in their model, so they feed these parameters, they get the exact tilt or shift of atoms. And also, yeah, by the way, at the end, they also discuss something about quantum spin liquid, like arrangement of magnetic moments, because in general, this idea of local deformation is connected to the idea of like having spins arranged or not arranged or correlated somehow. And maybe it can be possible, it can be used by someone who knows or thinks about quantum spin liquid in tantalum disulfide. But it's like half of page totally in the original article about it. So we also discussed something about this, but it's I don't remember some important conclusions about quantum spin liquid. It's just some data that maybe can be used by some specialists. Okay, so that's the article in a nutshell. Basically, that's the table of contents that we are going to go right now. And I really hope that the stream will be less than 3 hours, because it takes really a lot of time to discuss all these little tiny details, comment, figures. And in this article, my comments even bigger, okay, sometimes bigger than the sentences themselves. So it's not actually 7 pages, it's actually, okay, it will be a distraction if I open the table. Okay, that's not, we can count like this. So totally it's actually 20 pages. So in order to get through 20 pages, we need to be fast, and that's why I hope not to spend too much time on some not essential details. So, okay, let's start the discussion of the article from the abstract. Okay, so I forgot to tell you that polarons are not only there, but also there at the high temperatures. And that's also an important conclusion. I mean, what is important, what is not, you can judge by yourself, but that's the conclusion which was not known before. Because before people thought that in metal case, at high temperatures, there is a symmetric phase where there are no distortions, but here they found that no, there are still some tiny local distortions, which they explain as polarons. And that's also one of the important conclusions. Okay. That's what's written here. So the abstract goes like this. We have electrons, we have lattice, then in some cases there are polarons. Okay, at this point, I remember my discussion a long time ago with one expert of polarons, and it's actually important to know that polarons can be in semiconductors and not in metals. However, here they prove that they are in metals. That's why it's actually interesting, like results which make us think about theory. And okay, you might ask why polarons can be only in semiconductors. And to answer this question, to remember that discussion that was, I don't know, maybe 5 months or 6 months ago. Okay, let's just keep this discussion because no one writes comments in the chat. So in general, my idea is that because when we speak about polarons, we use like theory of free electron that moves through lattice, and that should be one separated electron. So if we have a valence band and conduction band, then we have few electrons traveling and a lot of electrons sitting. And that's why this whole picture is applicable. But if we have a metal, then there are a lot of moving electrons, so they interact one with another. They influence lattice in a different way, in a way stronger way, or they just like exhibit behavior of block functions. So different physics. So that's general understanding. The next level of understanding is based on Abrikosov Gorkov-Zelenshinsky book. So you can ask ChatGPT something about it, like upload Abrikosov Gorkov-Zelenshinsky and say, where are the theory of polarons? And that typical theory, okay, I don't remember exactly in that book, but the idea is that we do the transformations of the Green's function, and the typical like renormalization of mass originates from the Green's function that corresponds to electron, like one electron, not the electron in the metal. So that's something that I remember, and that's the best thing I can comment about this first sentence. But okay, yeah, sometimes there are polarons if we put electron in the lattice. And there is also theory of charge density wave and spin density wave, and they also give similar predictions actually. So it's a typical discussion of why do we need to use polaronic theory and not charge density wave theory. And okay, there are no clear answers in literature. And it's also related to the question, what do we mean in terms of formulas of charge density wave or polarons? And there are several options also. Sometimes people just work with Hubbard model, and the question of charge density wave or polarons is left somewhere behind. But okay. There are other theories also. That's the main thing that's written here. And okay, I have already announced that they study distortion using pair distribution function. So they use X-rays. I even don't want to think why exactly X-rays, because it's related to the question of pair distribution function, and there are a lot of questions about it. So that's what we're given, that exactly X-rays are used for all this analysis. And they do this analysis for different temperatures. And okay, there is some peak there in the PDF, which we will discuss later and maybe not see later because I don't remember this peak from the from any of the plots that are in the article. But okay, this one peak at the proper position. Okay, maybe it's actually this one. That's the best image you can think about. So somewhere here there is a peak which is not fitted by the just homogeneously distributed, I mean, the model that sees homogeneously distorted lattice. So that's why there are local deformations, and that's why there are polarons. So that's about this. And okay, we also call it Wigner crystal-like state because electrons are localized, and the Wigner crystal state is also about this. But like, we don't need to understand Wigner crystal in order to understand this paper. Just a comment about applicability of one framework. And also they say that some other well-known ideas like Fermi surface nesting or electron phone coupling is not what they see, or how it's written here. It's not what can be used for derivation of these properties. So it's not clear which formulas they mean, but I guess everything is about the derivation of local properties. So with this unexplained methods, it's impossible to derive exactly that tiny results that they got. And that's the main idea. They don't explain this. It's just a statement. And it will be not explained throughout this article because that's experimental article. And also the last thing in the abstract is that they mentioned quantum spin liquid, and they will not prove that there is a quantum spin liquid because that's how science works. People don't claim something, they say that something is consistent with something. So maybe quantum spin liquid is not there, but something is consistent with quantum spin liquid. What is meant here, it's very unclear because quantum spin liquid is about magnetic moments, and here we're speaking about lattice deformation. So there will be a discussion that if you use some symmetric properties of lattice deformation, then you will get distributions of spins, and some experts in quantum spin liquid say, maybe joined this research and wrote that all this deformation is consistent with something that is predicted by that very advanced theory. But that's a purely different world, so we can maybe not even go there. We'll definitely not go there, but I don't think that it's a really important conclusion of the article. Okay, let's continue to the first subsection out of 4. The first subsection's introduction, then a lot of discussions of all of the plots, and then main conclusions, then comments about magnetic ordering, and then there are also methods, but it's a very short part of the article. So we are finally going to the first subsection out of 4, the introduction. So first of all, there are a lot of special effects in two-dimensional materials. There are some non-equilibrium phases. So yeah, that's important thing because there are equilibrium phase diagrams, but also you can manipulate these materials and get some non-equilibrium properties, and in scope of non-equilibrium properties there are also phases, and there are a lot of citations about this. Then there is a Coulomb interaction actually, and it's interesting to just think about how exactly it influences the material or its properties. And there are also interlayer interactions, which should be also connected with Coulomb repulsion. But okay, interlayer interaction sounds like also Coulomb repulsion, but that's how they formulated the sentence. So it's just a proposal to think about some electromagnetic interactions. Okay, like if you think about electrons, then you could think about kinetic energies, and the density of electrons influences their kinetic energy, and the electron-phone interaction also influences kinetic energy. That's kind of obvious. Now, if there is the bigger electron-phone interaction, then bands are narrow and there are polarons. These are general statements that are known about polarons, that there is renormalization of energy band. There are a lot of special formulas for derivation of this renormalization of energy bands, and if you want, you can comment and I will discuss them later. Maybe I will discuss them during the next month. Let's see. But that's the typical properties of the electrons, that sometimes they can distort lattice and together it will be a polaron, and in this case the energy band is way more narrow. Yeah, also, I mean, you can at this moment already think about like at which material is applicable, at which is not applicable, because not in all materials we have polarons, so something there is assumed, some special inner properties that make all this picture possible. I still haven't reached the question about why in one material there is a polaron, one in another material there is no polaron. We can attribute it to the strength of electron-phone interaction, of course. But, well, okay, what we need to think right now is that just there are some special materials, and luckily the tantalum disulfide is of this type. That's why all of this discussion is about tantalum disulfide. And yeah, if electrons are localized, then there are a lot of effects, which are more known as effects of tantalum disulfide, maybe. But also, I mean, like if you speak about localized electrons, that's a very big part of condensed matter. Even it's written here that layered cuprate superconductors are explained by localized electrons. So a lot of things happens if electrons localize. And we don't need to know this for this article, it's just a review of general things that happens in condensed matter. And yeah, like okay, now we think about TMDCs, and that's an example of TMDC, transitional metal dihalogenide, and there could be different arrangements of polarons in this material. Okay, Coulomb interaction plays an important role in this arrangement. And there are other ideas actually, like Fermi surface nesting, for example, or Chern density wave models, as was written before. But here it's just a mentioning of other ideas, so it's way beyond this article to understand how these ideas are connected with Coulomb interaction. So in some sense, they should be something very similar, because everything originates from, anyway, Coulomb interaction, but there are different frameworks, and let's just mention other possible frameworks. They were not using them throughout this article, just the scope of motivation of the article itself. And now we have citations for experimental observations of polarons and stating that there are open questions. So there are several review papers. I mean, I have tried to learn one of these big review papers. So a lot of things are done in scope of experimental evidence of polarons, but something, as usual, is not fully understood about it. And here is just an introduction to some other works. Okay, so throughout this article, I had the question, why do we need to study these lattice distortions? Well, maybe someone will need this. That's how I understand this motivation. But here it's written about this motivation also, that it's crucial for progress in understanding a wide class of quantum materials. So of course it's unexplained why is it so crucial, but here this sentence tells us that it's important, and it's not explained. Is it important? So I'm not convinced that it's important, but that's what they're going to do in this article, and that's the introduction to this work. Okay, now the next paragraph is about tantalum disulfide. It has a lot of phases, as I showed you just here. That's the typical phase diagram. There is also an equilibrium phase, which is called the hidden phase. There are citations about it. and okay, it equilibrates and goes away, so we call it quasi-stable. And yes, that's written here also, that there is energy barrier to which system will anyway finally go through and go to the lowest energy state, which is not the hidden state, but an equilibrium state. Okay, then we have citations for band structure of tantalum disulfide, and okay, the hidden state is already in the past. Yeah, it's not connected. This sentence is not connected with the previous one. We just continue discussing tantalum disulfide. The next sentence tells us again, okay, unfortunately, I don't have this plot in focus structure. That's why I need to open new tabs. That's why it's actually a good idea to finally develop focus structure, not to switch so many times. So that's the typical phase diagram of the tantalum disulfide. And here it's again about this, that there are some phases, phase transitions, and okay, that makes us assured that there is a strong electron-phone interaction. Why is it connected with strong electron-phone interactions, you might ask? Well, because maybe some theory is assumed, and in this theory there are some models, like Hubbard model, a Tate binding model, and all of them assume strong electron-phone interaction. So that's just a reference to something that is known from somewhere before. And it's not explained here, so we are just using some information that is well known for tantalum disulfide. So now if we cool, we get nearly energy density wave phase, then if we further cool, we get the insulating phase. And also maybe these are good citations for some measurements of this density wave phase. But again, this is the reference to all this plot and all this discussion of this paper, which you can find on this channel maybe 1 month and 2 weeks ago. I was already discussing all of this. So, yeah. So again, like in scope of introduction, we have an introduction to quantum spin liquid because there are other spins. So maybe there is also quantum spin liquid. So quantum spin liquid can be suppressed. Maybe, I mean, there was idea that it can be suppressed by layers, but they don't like this idea because there are some spin spectra and charge spectra. So something here which is not explained here, but we have a cited paper that discusses this argument and says that quantum spin liquid still should not be suppressed. And there are a lot of effects in quantum spin liquid, like in magnetic susceptibility, some spin-spin relaxation, spin lattice relaxation times. So that's just a list of them. It's not an important part of the article, so what we need to know is just that they are there. I mean, we can even not know them. I don't know why did they put this sentence here. It's just a broad overview of quantum spin liquid. Okay, now we are also we are again discussing the resistivity, I mean the material itself, and you can remember this plot again from that previous stream. about the resistivity. So there are some transitions and at low temperatures. Yeah, maybe here at around 50 Kelvin, there is again a transition of the resistivity. Actually interesting that all of this in the one phase. So actually it's an interesting question which I wasn't thinking before, so I need to write it. Yeah, I wasn't thinking ever about it before, that like here we have phase transition, I mean transition of resistivity and also the change of phase. Here also the same, but with hysteresis, which is not that crucial. But here we have this transition and we don't have a transition of phase. So maybe later I'll think about it. Okay, that's written here. And we also have lattice deformation. So before it was about the electron modulation, and it was called charge density wave. And we also have the lattice deformation, which is called stars of Davids. And that's what we're going to discuss a lot of times during this article. Wait a second. Okay. Okay. So, okay, also here we have the important notation which will be used throughout this article also, the notation of symmetrical group. So remember please this P3 bar M, and that's the symmetrical group of purely undistorted material. And then we will have also, yeah, it's actually written here that if you have a distortion in Star of David's shape, and maybe I will show you very soon, that's exactly what is shown here. That's undistorted, and that's the distorted lattice. So I'm not expert in this symmetrical groups, but this is the notation that is used. There is some idea behind this, but for this article, we can think about it as just a label. So these are the notations for different types of lattice configuration. Okay, so there is the Wigner crystal model that is used for localized electrons. And the idea is that, okay, I wasn't actually reading any paper about it, it's just the thing that I remember from previous discussions. The idea is that, as far as I remember, if there are a lot of electrons there, then they interact strongly one with another, and the potential energy is way higher than kinetic energy, and they become just localized. And there is a criteria for this localization when we divide this potential energy to kinetic energy, and the main parameter is the concentration of electrons. So if it's bigger than some threshold, then we have an insulator. That's why actually we have here an insulator, which means that the resistivity is high. So the RS is an important parameter in this Wigner crystal analysis. And okay, there is some idea about this transformation of RS, which is sketched slightly here. But let's not focus much on this because the article is very big and we need to also finish it. Okay, so I don't know what is exactly the conclusion from it, but that's what happens. And that's again the motivation for us to think about electrons as localized ones. Okay, so the main part of the article is that they measure a lot of times. I don't know how many times, uncountable number of times. Maybe they have measured all the diffractions. So that's about the analysis of David stars, or this deformation that they have introduced already. And before they discuss their results, they cite they cite some papers that do measurements of these stars of David's, but they are at room temperatures. So this is the first article that measures them at different temperatures. It's actually interesting to see these articles after reading this article. Maybe it will be way easier to understand this articles after this one, but I haven't done this. I just know that there are some measurements also at room temperatures. And this article will do it at other temperatures, and they will find that Star of Davids are also locally deformed, and there are polarons at high temperature, as was written in the abstract, and as I announced before. Okay, they also write clear implications for other material of current interest. So by this, I think they mean that other material can also have polarons or have some similar local deformations. But I don't see any clear implications from this research, because of course I wasn't working much with this, but I can only guess that by implications they mean that they can do similar analysis for the materials and see also similar local distortions. Okay, we have finished the first section out of 4. Now the sections about results. So we have the figure 1, which is already here and which you have seen a lot of times. So we will go through it a lot of times during the reading of the article. Okay, but announcement is that here, okay, maybe I'll better not even go through this plot, but okay, let me do it very fast. That's the resistivity. That's the parameter of atomic interactions, which is not explained, but it should be a well-known parameter that is used for the form factor of scattering. And they calculated it somehow, maybe by a very complicated transformation, but still somehow they did it. That's an important plot of the pair distribution function itself and the change of the pair distribution function. I don't know why actually there is this error. I don't think that this error should be here. Don't see any importance of this, but that's like typical result and comparison with calculations for undistorted lattice. I mean, of all these results for all different temperatures. That's how this results pair distribution changes if you decrease temperature by 10 Kelvin, and if you do it in the metal phase or in conventional density wave phase. We'll go through it later also. That's the theoretical prediction. So if you somehow input some averaged, like undistorted positions of the lattice, and you need to know everything about the positions of lattice actually to calculate this. I'm just thinking about that, like if the That's what I'm thinking about. That, and also I'm thinking about viewers who are coming to the stream and leaving the stream. So, like, I understand that we can calculate pair distribution functions somehow analytically at zero temperature, but first remember here that's calculated for the metallic case, so at high temperatures. So what is interesting to understand how the temperature is taken into account. So the first thing that comes into my mind is that maybe they have introduced these oscillations of atoms because temperature means that something is shaking, and then they average over these oscillations. That's what comes into my mind, but and maybe later I'll think about this more, how to take this temperature into account in analytical calculation. But somehow for some temperature they got this total pair distribution function. And I forgot to actually discussed it yesterday, that why the pair distribution function is negative. Let me try to remember this. Okay, let me write it because I forgot. So it can be negative because, of course, there is a formula that's assumed for this PDF. But what is the meaning of negative PDF? That's the question. Maybe I'll think later about it. Okay, and the final plot, which is the plot number F, it should be actually F. No, yeah, but there is no letter F, but it's assumed that it's plot number F because F goes after E. So that's the collection of actually all the PDFs. That's the result actually. So it's actually a very informative plot. And that's also a place where we can see that there are actually two experiments, one for these temperatures, other for another temperatures, because for some reason we're limited in scope of one experiment and in scope of another experiment. That's this letter F actually. So this is maybe the main result, the initial result before we do this analysis or derive extra properties from this result. Okay, so we will go through all of this caption to the figure during reading the text, so I need really to save time. Okay, so the stream is nearly for 1 hour already. And I don't really want to do it for 4 hours, so let's return to this caption during reading of the article. So, okay, they did PDF at different temperatures. They saw different phases, and the final phase is the very high temperature phase. It actually has not 1T but 4R symmetry, which is a stack of 1T, 1H, 1T, 1H symmetry. It will be discussed later. Okay, then as I introduced before, there are some displacement parameters that are assumed that take into account these correlations. And it's not explained here in the article how they obtain these parameters. They're just given their values. I mean, the value of one of them, and other values are... Okay, another value is also written somewhere here. Okay, for example, here, U33. So again, that's part of assumed PDF theory that is only referenced. So for this article, we need to understand that these are the parameters that are present. I mean, it's an important question, of course, what is the meaning of these parameters and how to derive them. And okay, like if you really want, then we can open some theory and see some formulas. So they are atomic displacement parameters, also ADP. And the idea is that, where is this? So there is a scattering factor, and the scattering factor depends on basically these parameters in the exponent. So that's where these parameters enter the whole formula. And it's not enough to understand how to calculate them and how to fit them, but that's already something that I can tell you about it. And anyway, to understand really well this article, you need to really work out several articles about PDFs. Luckily, they are cited here, so if you really need, it's not that hard. It will take just a week, but I don't plan to spend a week on this. For me, it's fine to know that there are some displacement parameters that are fit in a clever way, because all of these are obtained by clever transformations or clever fit. So you can ask not this, but also like 10 or 20 questions about these fittings and obtaining of some parameters. Okay, but these parameters are obtained. So in plane component of this atomic displacement parameter is bigger than out of plane, but if there was a disorder, then it should be opposite. That's why there is a disorder in plane and not in between planes. That's a conclusion that they make from calculation of the parameters. I mean, this parameter of atomic displacements. Yeah, again, I wrote this reminder of the notation P bar 3m that I have just introduced recently. And there are David stars at low temperatures. That's what we already know. And yes, of course, if we change the temperature, then David stars changes and the charge density wave changes. That's what we'll discuss throughout this article. We'll see, for example, here on the figure 2b, that's how peak of the PDF changes with temperature, and that corresponds to the change of the distribution. And also there later we will derive exactly all these parameters of the change of Star of David's. So also like at high temperature there are also some distortions. That's why we say that there are also polarons at high temperatures. Forgot what is the word itinerant, but okay, it's written here that like metallic phase is the homogeneous state plus some fluctuating Star of David distortions. That's what is obtained in this paper, not the just homogeneous metallic state. Maybe before this pair distribution function, it was impossible to measure such precise these distances. That's why people thought that it's symmetric state, but actually no, there are still some distortions. Okay, here there is a figure 2, but again there will be a big discussion of figure 2. So here I will just briefly run through it. So as you know, like with the diffraction, so we get the diffraction peaks, and with clever transformations, which I showed you briefly, we get the G function. Yeah. So we also have this dependence of this one peak, so it grows slightly. And that's the close-up of this image. And okay, I forgot what is this. Maybe it's also a close-up of some peak. Maybe here, this one. It's function of temperature. Yeah. Yeah, I was thinking actually yesterday how this B and D are connected. And 3, 5. So maybe here we're just focusing on different temperatures. So this is basically the same plot as here, the main pair distribution function. That's also a main important the main parameter that is calculated the pair distribution functions. And this is the close-up with some features like tiny shoulders or tiny peaks. And we can see them for different temperatures, for 600 Kelvin, for 750, and for 15, and different feeds for 15 Kelvin. So that's what will be discussed in the future. And as I said, there are a lot of parameters, and this experiment gives us all tiny details about the displacement of atoms. That's why I'm still surprised that this experiment can ever be done, because it's very hard to get such all tiny distortions that are obtained somehow. These are very tiny parameters, and it's still possible to extract them. So that's something that's written here. The caption to the figure. So I have discussed something like this, but we will again see all of this through the text. So it's better to just continue the text. But now we approximately understand this second. That's not the second. That's the second figure. Okay, and as you have already understood that. We don't not only get the pair distribution function, we also do fit, and this fit has a lot of parameters, so we can see what is exactly the contribution from each of the atom to the pair distribution function. And that's something like which can be expressed by this formula, that the pair distribution function is the sum of several pair distribution functions. And okay, we will see later. We can actually see them right now. But later there will be a discussion that this is the influence of different pair distribution functions. So tantalum atom influence is way bigger than other interactions between atoms. Okay, maybe it's better to say correlations, because everything is about correlations somehow. So we are deriving the correlations. So how exactly to distinguish this? That's an advanced understanding of the article that I haven't reached during 2 days of my preparation. So what is important is that where is this plot? To be this plot. So in this plot, the pair distribution function has a shoulder. Okay, and that's because of tantum interactions. I can be wrong on this place because there is some special discussion of this shoulder. Let's first remember that's because of tantum pair distribution function. Okay, there is also figure 1e. And maybe if you look at this figure, then you will see a peak exactly at tantum atom. That's how I understand this. So let's check. Okay, I just changed this phrase because seems that I believe that that's calculated here. I didn't check. I'm too lazy, but that's what is written here. And if you don't take into account Star of Davids, then oh my God, we have a first comment. Oh my God, I have to read it. Oh, thank you, United9. So you're the first one who ever wrote a comment. That's a important day for me after 1.5 months of streaming. Yeah. Thank you for your support. If you have some questions, you can ask them. I'll try to answer. I don't know what is beef, unfortunately, so I can't tell you what is my opinion of beef. I'm not native speaker of English, unfortunately. Okay, but if you have some questions, just write them. I also see that my chat on the top is not working. I need to think about it. Actually, all questions should be there at the top panel, but they're not appearing there. Okay. So let's try to continue somehow. Distortion. Unit title. Okay. So, okay, we know the contribution of tantalum atoms, and just a second. And yeah, also maybe they actually should be dynamic. That's why I wrote this question about temperature dependence, because temperature means that there are some fluctuations, and but okay, we're not having any discussion of time dependence. It's just maybe a side comment that there should be fluctuations. Of course, they should be there, but I don't know why this sentence is here at all. So, okay, here citation is for special distortions. So we actually already they have calculated this already. So maybe that's the cited paper that relates to these calculations. And this paper maybe confirms that this should be peaks that they calculate. Okay. Confirm. So, okay, if we look at the charge density wave phase, if we do this pair distribution functions, then we can fit the model by the calculation of pair distribution functions from like distorted lattice, like this one, where there are stars of Davids, and with undistorted lattice. Yeah. So that's what is written here, that they just do another fit works better. That's why there are stars of David's there. One of the proofs that they are indeed there. Okay, of course it's very complicated to calculate this, but this is the application for this calculation. I mean, so that's like complicated part of the article, because you might want to have some analytical derivation, but it's not here. You need to just read the paper about this, maybe Python or some other programming language program, and that's the only way you can understand this analytical derivation, fortunately. So I can't explain you something more, except that we're having the results that the fit is better for the distorted lattice. That's an argument that there is indeed the distortion. Um, I'm trying to understand this second sentence, that because there are domain walls in other phases, for example, different arrangements, and okay, maybe that's advanced understanding that if we have another lattice, then like another phase, then there are other features and we can take them into account by adding also undistorted lattice. So why is it so? It's not explained and sounds like a strange statement, but we will go to the statement later. It's about the fitting and there will be a distorted percentage. So that's how they always do averaging all over a lot of atoms, and like if you have a weighted averaging, so you say like some percentage of the material is distorted, some percentage is not distorted, then that's how it's also possible to explain the PDF. Yeah, and we will discuss all of the results below. Okay, so the first actually paragraph in the section of the results. So introduction of the results is what we have done. Yes, there are a lot of stars of David, so on. PDFs for different types of materials, some parameters that are extracted. So now we will go through phase after phase. So the first phase, which we are looking at, is the polymorphic regime. So this is the higher temperature case. So at high temperatures, we have several phases at the same time. That's why we also will call it 6R symmetry. I don't know why 6 and why R, but that's the label of this high temperature phase. So that's the statement that is here, that there are several phases. And these phases are stacked on top one of another. Oh, what is interesting, which I wasn't thinking about before, that there are changes in the pair distribution functions also at high temperatures, but it's like left for supplementary information, so that's why I wasn't thinking much about it. But interesting that we also have this change of PDFs. And this shoulder, which is important observation of the whole this article, is also there at the high temperatures. But let me write this question about which I just wasn't thinking before. Okay, maybe there is some phase transition. I don't know. We're not having much discussion of this. It's just, I mean, we have just some sentences about this very high temperature phase, and there is still shoulder. There are some. Is it read like this? I don't know why did I write that PDF changes abruptly. Okay, I just need to delete this. Changes. Okay, that's maybe my bad comment here. But okay, idea is that something is here. Transformations in PDF data. Okay, so the distorted fraction drops at 630 Kelvin. So distorted fraction is the percentage of the distorted part of the material comparing to the undistorted. By the way, I forgot to click like this. Okay, so it's 730 Kelvin. The 6R, that layered different phase structure, is the good fit. Let's see this figure 2C. So that's about this. So that's the high temperature per distribution function that is meant here. So 6R is this layered configuration of different phases. And what happens here? Okay, so it explains well, but there are some local distortions. So that's why, I mean, so look, what happens here actually, maybe we need to discuss this plot. So we are dealing with high temperatures. So what if we have, maybe we need to look at exactly this plot. So what if we have two phases layered after layer? Then that's the symmetry that we work with. And if we do the fit, then we are getting actually a very good fit. But there is something that is not fitted. But why is it not fitted? That's because we have some local distortion, and local distortion is not taken into account this purely symmetrical model, and that's why we say that there are also polarons. So that's the important message here. And this distortion fraction tells us that just in 10% of the whole amount of mass there is distortion. That's what I think that is meant here. So and maybe the sentence also about this plot exactly because yeah, that's as written here that we do this calculation and then we compare with the experiment. Okay, now we have also figure 3 that we will be using later, but the idea is that we have a lot of parameters here, and they're shown here on this plot. We have angles between stars of Davids, we have two angles inside of stars of Davids, and what if we change the temperature? Then they will change. So this angle, this angle, this angle, they will change according to this plot, or this plot, or this plot. We also have some distances, and the distances will be changed according to this plot and this plot. So there are several atoms. They are shown here, first, second, third, and this is the distances between them. I mean, in scope of one star of David, these are the distances in between two stars of Davids. That's why they are higher actually than these ones. But we see that David stars are very close one to another. And like if we change the temperature, then they are increasing. Some of them are decreasing. Some of them are nearly constant. Maybe they have some comments about it, which we will see later. So that's about the distances. Now, which of them are locally distorted? How many of them? Well, this fraction is shown here. Yes. So we are coming to the one. So okay, let me write just this question here. I mean, if we go to the one, then maybe it means distortion fraction, how many stars of Davids are there. That's my interpretation. So maybe there should be somewhere another parameter like local distortion fraction, and that's just distortion fraction. So that's the star of David. I mean, existence of it. Oh, we have even one like. That's a big achievement. I like during the stream. So that's all about this. The red and blue shows the heating or cooling. That's rather obvious. And this is the close-up of this plot. So if we look at low temperatures closer, then this plot is, I mean, these parameters are in this plot. And if you look at these temperatures, but for just one, okay, for three distances, and again cooling and heating, then you'll get this plot. So it's rather easy, and this thing which will be discussed later, it shows that there is some error in fitting, and this error decreases if you use two-phase fit. That's the place of the phase transition. So we will again go through all of this plot later. There is actually this weighted distortion, the formula for it, which was given by ChatGPT. So that's like distorted and distorted fraction. Yeah, so, okay, I need to erase this question. And it's not the question, it's just my comment. What do you mean about distortion fraction? Let me write it here. So I have added this comment here, and that makes sense. So, okay, the question is then, how do we call? Yeah. So maybe later we'll come to this question. Okay, here there is a discussion of all these parameters and discussion of these plots, which are rather obvious. To decrease temperature, then it goes to the fully distorted Star of David. I mean, fully distorted lattice, which we associate to fully symmetric Star of David. And there are also these vectors that are used for the direction distortion, but all of this will be discussed in the text. Okay, so the takeaway of the polymorphic regime is that there are different phases. I mean, there are two phases, and they're stacked one of another, and this is what fits the best pair distribution data. Also, it changes somehow at the high temperatures, but it's not explained in detail how. But also, what is important is that there are even polarons here, because there is a shoulder which can be explained only by local distortions. Okay, now we are cooling the system and we are going to high temperature metallic regime. So it starts at 600 Kelvin. I mean, the metallic regime, yeah, it's around. I mean, okay, like very high temperature phase, it's also metallic, but here we don't have maybe two phases of the distortion of atoms. Yeah. Uh, I wrote a bad comment. So, okay, there is some peak. I mean, it's not just my bad comment, unclear one. It's also the text which tells us that there is some peak. And okay, this plot was calculated for. Let's see. Okay, there is some peak. I don't know which peak. It's not explained here, but I thought it's actually about this calculation. So we have a prediction that there is somewhere a peak. To see. Okay. Okay. So it's better to look at this figure. That's the plot for 600 Kelvin. 1C is this one. Okay, that's the pair distribution function that is obtained exactly for 600 Kelvin. That's the correction of it comparing to the full and distorted lattice. So we conclude that there are some local distortions, and if we look, so this plot should be exactly actually this plot, this one. So if we look at this one, so how many peaks do we have until 6? Like 1, 2, 3, like 4. 1, 2, 3, 4. So it kind of works. I mean, before 10. 1, 2, 3, 4. 1, 2, 3, 4. So that's what I believe, that this plot is exactly this plot. Yes, and what is RW? That's the thing that I have asked already 3 or 4 times ChatGPT, and I fortunately don't really remember right now. Maybe that's exactly this number of distortion of how many local distortions are there. Or maybe, like, when there are two options. First option is that how many stars of Davids are there, and the second option is how many local distortions of stars of Davids are there. And okay, that's this RW. Okay. Maybe this RW for both of them. It's just not written for which of them. So as you can see here, there is here a plot for distortion and not distortion. So for distortion, this error is way less than for not distortion. Okay, and that's the idea here. Maybe that's the not really complete sentence, but that's exactly the idea. Okay. So this local distortion is around 5 angstrom, somewhere here. I don't know why. So maybe why 5? That's why I told in the beginning of the stream that it will be a long and complicated stream, because there are a lot of statements and I have already forgotten what is meant here. Okay, let's maybe try look here. Okay, like my version is like this. So by distortion we mean just charge density wave modulation and just symmetrical stars of Davids, and we're not discussing local distortion at all. So if we look at this plot, that's the like misfit of the symmetrical case, calculation for symmetrical case, and real partial distribution function. So we say that here at the 5 angstrom there is a big misfit. So this is the distortion, which is somewhere around this 5 angstrom, somewhere there. Maybe a lot of atoms are displaced such that there are big correlations between them in the range of 5 angstrom. Then there are still distortions here at the range up to 10 angstrom, because there are still some distortions, and after like around 10 they are nearly absent. Okay, that's my understanding. And okay, the next sentence explains the same thing which I told you, so maybe I'm right. And okay, so that means that there is localization because all these distortions correspond to the localization. And that's what was already announced before. Okay, why do we need 1D plot? Okay, there is also, I mean, we have discussed this misfit. There is also 1D plot, which is mentioned here, but don't see that it's really important. Yeah, we can see the subtle changes, but I don't think that's relevant for exactly this place. Localization is not stores. Okay, so the idea here is that yes, some electrons are localized, but we don't have this this picture of stars of David's, like this modulation, because there are so little number of them at high temperatures. Okay, 1D and 1E. Okay, so here there is a comment about these two plots, which is not what I really understand, but some fluctuation of charge is also there. That's why I don't understand, because it should be 2D. Yeah, okay, I need to change it. The typo. So in the figure 2D, what do we have? Let's see at this figure. Oh my god, we haven't ever actually discussed this figure 2D. I discussed 2C figure, but that's the figure 2D. And I need to tell something about it in order to explain this. Yeah. So if we look at 3.3 angstrom, so somewhere here, there is the broad peak, right? And that's because of some fluctuations. Yeah, and nothing is really clear, but there is just a statement about this peak, which is not connected to the previous sentence. That's how I understand this. Okay, now there is this image of distortion. So as you already know from this whole discussion, there are a lot of parameters of distortion, and that's another illustration of them. So they can be distorted out of plane, in plane, and with different angles. So now we are told to look at this plot. Why did I write this comment? It's very clear what happens in figure 2G. Okay, so this the distortion parameters. Okay, so now, okay, the same weighted average into C top. Yeah. So yeah, that's the idea that I have already introduced, that if you add distortions, then you calculate again weighted average. And that's the answer actually. Distorted fraction. Yeah. So it's clear that distorted fraction is the same parameter, but the question is that comparing to which model we calculated, and if we calculate it for the model with local distortion, then we can see this better fit. That's the decrease of the local distortion percentage. So that's the great achievement. That's why there are local distortions. And okay, the weighted percentage is 10%, which is locally distorted. So this is more precise information of something that I have already introduced before. And the only thing that I really don't understand is this, like the sentence, the light red profile in 2D and the intensity band in 1E remain broad, consistent with incoherent distortion from weakly developed fluctuating charge correlations. So, okay, let me write this question here. Okay. But some idea and some complicated method is assumed here. That's why they say that it's not a problem that they have a broad peak. Yes. Yeah, intensity breadth in 1E. That's so 1E is this one. 3.3, so it's somewhere here. Okay, I mean, red profile. Okay, I just want to finish this and 2D. That's the red profile intensity bed. So okay, because we're speaking about high temperatures, so that's the red line that we need to see. Okay, I'll just write that it's very unclear what is meant here. So it's a very unclear sentence. That's just a comment about this plot, for example, 2D, that some fluctuations are there. That's why peak is not very precise, but a little bit broad. Maybe we need to just forget the sentence because no theory is written about the fluctuating charge correlation. So that's how I propose to understand the sentence. Okay, now we are cooling the system even further in commensurate regime. Yes. Now we'll look again at the red lines because basically that's about incommensurate regime. Wider misfits. Now we need to look at the 1C figure. 1C. Okay, that's the figure 1C. There are bigger misfits. So when you look at the 1C, you need to look somewhere here at ICCDV, so 400 Kelvin. Here, the misfits are not bigger, but here they're slightly bigger. That's what written here. Now we look at figure 2D or 2E. Because, okay, yeah, remember the 2E is the same as 2D, but for different distances. This is for lower distances, this is for higher distances. And let's look at the peaks. And they are sharpened if we cool the system. Okay, we need to just believe because we don't have data for even higher temperatures, but somewhere there is this data, so peaks sharpen. And if we further cool, then it will sharpen even more. So it makes sense. And that's what written here. that at even low temperatures that even they will be even more sharper. And now we again look at somewhere here, this position. Okay, no clear peak at high temperatures. So, okay, there are several features. For example, here there is no peak at high temperatures, because if you look at the red line that goes like this, later at lower temperatures we will have a new peak. And I wasn't thinking about exactly this peak, so I can't comment you more about the meaning or interpretation of existence or not existence of this peak. And also we have something here. We also don't have a peak at high temperatures, but later there will be another peak at low temperatures. And maybe also here, actually here there is the peak of high temperatures. What is meant by separated into distinct tantum distances? Why did I write this sentence? Just I don't know how it did appear. Yeah. So, man, maybe ChatGPT helped me somehow, but it's a bad idea to have some comment which I don't understand. So the idea is that, yes, there is this broad peak. Okay, that's good. Let's go further. I mean, there is interpretation of all of this, but it's another big work to interpret it in a good way here. We just need to see this and just remember that, yes, that's the important feature of the results. And okay, at higher distances, there is opposite thing. So here at lower distances, peaks becomes what? They're not there, it's like white, but at higher distances, peaks with temperature increases. And okay, maybe, yeah, it's maybe better to say that peaks are sharper than comparing for the lower temperatures. Okay, so if peak broadens when we cool the system, then there is more chaos or less correlations, basically, in this like inter-Star of David cluster. Okay, we also have this notation of broken symmetry, so on. It's a confusing how to say, label of something, but the idea here is that there is the Star of David symmetry, and if it's not that symmetric, then it's called broken symmetry. So nothing more is meant by this statement, this phrase. So we also know that there is this localization. So if charge is localized, then I mean we know that charge is localized. That is consistent with the change of the peak. Yes. Yeah. Okay. What is worth of mentioning here that, yeah, we need to look at this plot, figure 1b. So we have not just the change of the parameter, but I mean, we should look somewhere here. This is the temperatures that are of current discussion. And the idea is that it's not the change of the parameter, it's the change of the slope of this parameter, because the change of parameter itself is expected because we decrease temperature, but change of slope is something that's not that expected. That's why it indicates localization. Again, some advanced connection of this parameter and the positions of electrons is assumed. Uh, okay, so we do the fit at this point as far as I remember. So we have figure 3a, that's the resistance. So we are, where are we? Somewhere here, 350. So that's the change later from incommensurate to near commensurate way. Yeah, so we're discussing this regime in commensurate density wave, and here we will have the change of resistance. I mean, but here that's the temperatures that we are looking at. So I think that's not actually connected at all, this resistance. And I mean, directly not connected at all. Because resistance is one thing and localization of lattice is another thing. And it's not, I mean, from localization of lattice, we can't derive the change of the resistance. Yeah, it's another story about how to derive this resistance. It goes beyond this article, definitely. So in the incommensurate density wave, more atoms are distorted. 30% of them are distorted. We can look at this figure 3, number C. That's this number. So here, that's what we're talking about, 307 and 50. But it's about, again, already changed to the commensurate, from nearly commensurate density wave. So later we will have way more of them distorted. Currently we have incommensurate density wave. So okay, here next sentence tells us that, again, like if we look at the, oh no, we have a figure 4 for A. So if we look at this PDF at high temperatures, then the peak is broad because different atoms have different shifts of, like tantalum atoms, different stars of Davids have different shifts. That's why we have averaging and we have a broad peak. Uh, Also, we have discussion of interlayer stacking. And okay, that's also connected to the name of incommensurate density wave, that the layers are distorted, not like in commensurate way. So that's also related to the broad peak, but I think that's about this plot. So in this plot, you have a broad peak, and that's why you have different stacking. So that's why that's incommensurate density wave. That's how I understand this. The center of this distortion is somewhere here, 5.9 angstrom. Okay, for some reason it's written here that by this peak and this peak, they correspond to interlayer stacking. And that's a little bit surprising because I thought that that's only the one that corresponds to interlayer stacking. But Okay, somehow it works like this, that layers are close one to another, so this peak and this peak, they both correspond to interlayer stacking. And also we have this and also we have this position of this peak. And also, okay, there is this negative thermal expansion and positive thermal expansion. So when we change the temperature, what happens? The peak shifts here and here. So that was the position of peak before. I mean, when we cool the system, then it shifts here. So temperature goes down, peak goes, the distance increases. That's also what is shown here. Then we can interpret it as the change of the different distances, because we have the program that has some like parameters, and we can like put a new parameter, like slightly new distance, calculate the new peak, and then it will fit well the, I mean, calculate pair distribution function, and that then it will fit better. So in that whole calculation, it's assumed that the peak corresponds to the distance. So if we have a shift of peak, then it immediately means that the distance between some pair of atoms is changed, increased or decreased. And I can't explain that this and this is between several layers. Intuitively, only this should be between several layers, but okay, that's how layers are stacked one on another. It's also very hard to distinguish the distance between them. I mean, which peak corresponds to which interaction of which atoms. Okay, this shift is what I have discussed, and okay, there is a figure 4, which shows the close-up of, it should be actually the same as somewhere, for example, let's see here. If we look at, okay, that's somewhere here, from 5 to 6, that's one peak. So that's the close-up of this plot of the figure 2, right? 5, 6, 5.6, it's from here to here. Yes. -2. Yeah, looks very similar. And this is something that is obtained, by the way, ways. So this plot should be actually close up of this plot. So it's from 2 to 5, from 2 to 5. So that's how I understand this connection of these plots. And that's already for higher distances. Okay, but this intermediate plot, so this one is between this and this, somewhere here in the middle. So don't see it. So, but okay, we have actually this one plot. So if you look somewhere here, from 13 somewhere here, so that's maybe exactly this position of this plot. Okay, another PDF. Then we subtract from this PDF the PDF at 500 Kelvin and get this subtraction for different distances. Then this image shows the different like interactions. So there is interaction in between one bilayer, or in between the second bilayer, or between two bilayers. And okay, this will be also used for analytical calculation of pair distribution function, because their clever program knows all the I mean, can take into account all the distances. This will be used for us in the later last part of the stream, when we will be discussing magnetic orders, and this is the direction of possible magnetic moments. And there could be something that looks like quantum spin liquid in plane, and something not like quantum spin liquid in between planes. And magnetic orderings can be somewhere. Some of them can be used. Here it's a schematic illustration of the clusters that are there at different temperatures in different phases. That's what's written here in the caption. So we will go again through it, so I don't need to read the caption. Okay, so as you can see, nothing is really very, how to say, extremely unusual in the paragraph of uncommensurate regime. There are some peaks, there are some parameters, there are some shifts of the peak, and there are some ideas about origin of the peaks from interlayer stacking. Yeah, so no exact conclusions are done, just a description of some plots that are also there. I mean, some are there, like figure 2, figure 3. Okay, now we're cooling system even more, and here we will see the nearly commensurate regime. And that's one before the last. Like there will be a commensurate regime. Let me just check how much time the stream is going. 2 hours already, and that's why I said that I really hope to finish it in 3 hours. We also have a discussion, but okay, we are coming to the end. We did more than 50% already. So, okay, the pair distribution function is bigger in nearly commensurate regime. We need to look at the peak at the plot 2D, because now for the temperatures NCCDV, like it should be actually of the dark red color. So, okay, 3.25. Okay. Okay, so here there is the peak, and I mean, at very low temperature, so I don't know why did they write it about in commensurate regime, because we need to discuss the commensurate regime, but there is this peak. And there is also a peak somewhere here. So here, this appears first time ever when we cool system from the incommensurate chart density wave regime. Okay. I was confused. Incommensurate is something that was before. Okay, so that was right. Okay, because the problem that I was looking at the little bit wrong plot, that's also the right plot, but that's the close-up, and we need to look at the close-up. So 325. So before we had this peak, and later we have several peaks. That's what's written here. Like, for example, this peak, and this peak. And before there was just one this peak. That's the main idea of this sentence. So this one, the first peak, corresponds to interactions inside of the cluster. That's expected because that's the smallest peak, the smallest distance. So two regions with domain walls between peaks. So you see, it's very hard to understand what they really mean. That's why it took me 2 times more time than I expected to prepare this article for the stream. So it's like residual intensity at 3.4 angstrom. So where is this? Like, we don't see this residual intensity, right? Okay, maybe we need to look here somewhere, right? I don't know. That's intensity. 3 point, but that's already inversed Q. I mean, Q is an extreme -1. So it's not the plot, definitely that's not the plot that we need to look at. We need maybe to look at this plot. Commutation approximately. Okay, I need to conclude it somehow. Okay, I need to just rewrite it. It's a very unclear sentence. Okay. Okay, sometimes it happens that you don't understand at all what they really mean, because what is meant, like what is this peak? No way to understand it. Let's just keep going. Okay, so figure 3C, it's not this one. So I mean, so the statement here is rather clear that there are this, I mean, typical plot of nearly commensurate density wave is this one, that there are clusters of stars of Davids, and there are big domain walls between them of fully symmetric lattice without any distortion. That's well known, that's written here. They say that there is some intensity somewhere which corresponds to this configuration, but it's not clear which intensity, but in which plot. Then it's written that this like simulation of two these phases, that it reproduces the fit well. I mean, it reproduces the PDF well, so if we take two phases into account, and two phases are this basically like the one phase and another phase, so that's somehow how they take these two phases into account. And as you can see here, like if you have two phases, then the fit is better. So what is this parameter? Maybe that's parameter that reflects the error that is obtained when you compare theoretical results in the experiment. And here you explicitly see that if you have non-commensurate charge density wave, then you need to have two phases, which is really obvious because like we know how nearly commensurate charge density wave looks like. But okay, we can also do it. Deduce these results from pair distribution functions and function, and that's the result of this comparison. That's what written here without any extra comments. Now, okay, if more Star of Davids appear, then there is a bigger distortion. 3A. So if we look at the 3A, there is intra-atomic sites. So we need to look only here. And they don't actually increase much. They increase very little. So I don't agree with this statement. We are anyway given the figure 3A. And what is B? B is the close-up. So some of them increase, some of them decrease. And figure 2D is this one. So somehow it's consistent. So like you see, the peak becomes sharper, and here it becomes sharper, and here it becomes sharper. So it's also not explained. It's written that it's consistent, but maybe it's even not connected much. These are just two results that we'll have. Okay, except this abstract unexplained comments, there are more clear statements. For example, that there are changes of the Star of David, there are angles, so suddenly they are rotated also if you decrease the temperature. And you calculate the pair distribution function as a sum or weighted sum of pair distribution function, which corresponds to several arrangements. I mean, that's obvious, right? Because that's the nearly commensurate density wave. You have different regions, so and also that's another illustration of nearly commensurate density wave. So like you have contribution from one phase, from another phase. Then if you decrease temperature, then this contribution changes. The one contribution becomes bigger, another contribution becomes smaller, and that's information about this. So again, the same comment about nearly commensurate density wave. So here I wrote a comment that it's good to read some experimental results of purely nearly commensurate density wave. Maybe it looks exactly like it's shown here, but maybe not. I just didn't check it. And here we're dealing just with averages. Yeah. So just a reminder for me to learn better what is nearly commensurate density wave. Okay, now the last comments are about the hysteresis, and to see hysteresis we'll look at the figure 3, B to E, where's the E figure? A, B, C, D, E. So, okay. So all of these plots are relevant. So yes, if we decrease temperature, then we have like one dynamics, and if we increase temperature, we have slightly different dynamics, and that's is what written. I mean, the comment about it is written here. But after this comment, we have another comment that there are correlations in B layers. and different bilayers have different stacking positions. Now we need to look at figure for A and C. That's figure for A. That's figure for C. So the general idea, which is not explained, is that like we know this bilayer geometry, and let's written here. Let's read again. Bilayer correlation. So maybe it's meant that these are how bilayers interact. There is a distance between them, and if we look at this distance, we will get, for example, this plot. I mean, this peak of pair distribution function, and uh, and that's how we know how the distance change. For example, as temperature increase or decreases. Actually, it's interesting question why there are two peaks here and there was just one peak before. What this meant by existence of another peak? Okay, it's actually interesting question. Okay, that's an interesting question. But here we have the discussion of this bilayer interaction. Interbilayer correlations are still fuzzy. Why? Well, an experiment, because maybe the peak is broader. For B and for D. Okay, maybe at these distances we have inter-bilayer interaction. So between two bilayers, and maybe this is in one bilayer. So yes, that's consistent with this plot, because this plot is about interaction in one layer, inside the Star of David, between Stars of Davids, and if we go further, then this interaction between two bilayers, because this distance is bigger than this distance. So okay, that's what I approximately understand. And here there is a broader peak between two layers interactions, because they are stacked in a not very symmetric way comparing to stacking of two bilayers together. Yeah, okay, so that's how I understand what's written here. It's, as you can see, it's not written very on understandable level, on a very understandable level. It's written very in a compact way, but okay, that's how I understood. So in a nutshell, Nirika measured Chern density wave. We have different phases and we have different peaks. Some of them are broad because like for example, there are different stackings of the bilayers, and we also need to have like weighted average, and then we can also feed the weighted average and see how much one phase is present compared to another phase. Now the last one, commensurate regime. Let's remind ourselves. Yes. Okay, there is this tiny section about symmetry of order parameter, which is rather more for theoretical derivation, because there will be distortion of lattice and there are some vectors which describe this distortion. Okay, we are finally reaching the last 40% of the stream. How much time has passed? Oh, we have 2 likes. That's wonderful. That's very unexpected. Okay. Commensurate regime. So that's the most symmetric regime where there are David stars. That's how it looks like. That's the general phase diagram. And here they will give us some additional information. First of all, we need to look at the figure 2D. That's this figure. That's this figure. So if we look at the 3.4, somewhere here, there is the decrease of intensity. That's what we are told here. And another peak sharpens, like this peak sharpens. Why is it consistent with increase of Star of David density? It's not explained. So, Spark made another typo. So that's the question here about this connection. Big R. Okay, now we'll look at this figure, the same for the bigger distances. And also there are some peaks that are sharpened. Okay, that's just the comment about this plot. So now we need to look at the green plots because that's the commensurate regime. Okay, so another thing that happens in commensurate regime is that atoms change somehow their positions, but I don't think that it will be very much explained here. I mean, we know that there is this increase of resistivity somewhere here at very, very low temperatures, but it's not connected to, I mean, I don't see this connection between this increase of resistivity and some additional rearrangement of atoms. Here, they just written that it's there, so we need to just believe this. And okay, yeah, we can look, of course, at the pair distribution function and see that there is another shift. Okay, and that's exactly what is meant by this rearrangement, that like we look at this tiny shift and we know that if we calculate PDF, then peak corresponds to the position of atoms, and that's why we know that there is a tiny shift at very, very low temperatures. So here maybe it's written that if you do this calculation, then you will get also this rearrangement. 3A and 3B. Which modeling? Okay, that's unclear sentence. It's not clear. The idea is that okay, I understand the sentence that if you do calculations, you will get these results. We are not given any information about what is the model in here. Okay, now there's something that is more clear. Then that, of course, we have some angle deformations. We have several angles, theta, beta, alpha. So it's also reduced, as you can see here. Actually, not reduced, but it goes to the very symmetric Star of David deformation if you decrease temperature. And also this one, okay, this beta is reduced, but I mean, okay, it's just the change of the whole lattice to the fully symmetric Star of David case, except that there will be some local deformations which are not discussed yet here. So yeah, that's what also written here, that this deformation goes to the symmetric Star of David type deformation, and then amount of Star of David clusters goes to 1 because all of this phase will be full of Stars of David. For B and for D. So here, maybe that's the answer to the question that I just wrote, that there is this additional peak that appears if we really decrease temperature in the commensurate charge density wave regime. That corresponds to the appearance of inter-bilayer correlations. So bilayers become more interacting one with another. That's what happens if we really cool the system lower. I'm just thinking that, was it written? Okay, maybe it was written that we're always working with the layered material here. So for one layer, they haven't done the experiment. Maybe no one has done for just one layer on a substrate. So I guess if it was one layer, then we would not have this peak here. Maybe we'll have some peak which corresponds to the interaction with substrate. Somewhere there in another place. Okay. And this peak changes. There is positive thermal expansion. So if you decrease temperature, then, I mean, if you increase temperature, then it will increase. If you decrease, then it decreases. That's what meant here. Okay, now we need to look at this plot and see that, oh, actually, between layers, there can be a lot of options how stacking can appear. And we can't tell in advance what is the correct one based on PDF because we have just the amount of, absolute value of the R distance between these positions, but we don't see information about direction. And okay, if we cool more, then there is this change. Yeah, so there are changes again of this peak, of this peak, so it changes, yes. But it changes only in the amplitude, it does not change in the position if we further cool. But here, if we cool, yeah, maybe it also does not change. Changes at intra-bilayer, so it should be this one. So what is meant? I said that it's not. Okay, maybe I was very short right now on the wrong sentence. So if you look really, really carefully, it shifts very slightly on one fraction of angstrom. which is really extremely tiny shift. So that's what's meant here. But if you look here, then it does not even shift on this little fraction of angstrom. I mean, that's what I understand here. 4a, yes, that's the 4a figure. Okay, you can look also for C. Okay, here it's more explicitly seen that peak shifts again on this little tiny fraction. And here it does not shift. I mean, or maybe it shifts, I don't know, 50 times less. Because, yeah, okay, it maybe does not shift or shifts very, very negligible. So that's what's written here. And okay, that gives us the conclusion that B layers can interact. All right. I should write it like this. Layers. Yeah. So that's why, because of this shift and not shift, there is idea that B layers interact stronger inside of it. I mean, layers inside of B layers interact stronger. So these are the collection of comments about the plots of pair distribution function that gives us some deeper insights of what happens in the Star of David clusters. So you can, as you can see, a lot of tiny details were obtained, and all things that are possible to be analyzed have analyzed. Unfortunately, not all the statements here are clear. The text is very compact, and it's hard to see what is the real conclusion out of this collection of the comments. Okay, we are reaching the end. Basically, we have 3 more paragraphs. The first paragraph is about symmetry for the parameter. So there are some distortions, and which distortions can be. So there are some symmetrical distortions that are introduced here. So here a notation of representations of space groups is used. I'm not sure how important it is to understand this notation, so I'm skipping this explanation since I don't think that that's really essential for understanding of the article. But if you want, then these are the names of the representations of this symmetrical group that is always there as like group of undeformed lattice. And I thought once about this notation P bar 3M, like mirror symmetry, some inversion, something else. But for me, it's just a name. I haven't reached understanding of this notation. Okay, now there are vectors that are proposed, and maybe I should open some plot that has them. Okay, it will be written here. What should I open? So here there was the plot. Yeah, maybe that's exactly the plot. Okay, somewhere there are 2 wave vectors, and these are the main wave vectors for the proposed deformation. So it's not an arbitrary deformation, it's a symmetrical deformation. Now we get the reciprocal vectors in terms of the lattice wave vectors. And somehow they use these reciprocal wave vectors to calculate okay, maybe it's better to say like this. Okay, if we don't okay, I need to write it better. Okay, so here they say that the amplitudes of the representations of the group are described by these reciprocal vectors. So as you can see, it's a very poor explanation, and I can only guess what's really meant. But somehow they use these new lattice vectors for the description of the symmetry, and that's the main idea here. And now we have the 3F figure, and that's what is already opened here. That's where somehow you can see the directions of the deformation of the Star of David. Yes. Okay. Now in nearly commensurate phase, there are deformations of like there are constants A and B, and these constants have particular values. So for commensurate phase, for incommensurate phase, and for incommensurate. So these are the values that were obtained by maybe fitting this deformation to the real displacements. It's also very hard work to do this extraction of this data. What we have is just the result that this is the value of the deformation. So some people, experts in symmetries and groups, have proposed all this deformation, and we don't have some intermediate stages. We have just the result. Okay, and that's everything about the local deformations, and we can't say something about long-range order because we have a lot of averages, and at little distances we have just the interaction between Star of David and nothing more. But if we look at the long distances, then there are a lot of averages because there are different atoms that have also these or similar distances in between them. So we can't say about the long-range deformation something particular from the pair distribution function, pair distribution data. Yeah, that's written here. So we know everything about the change of Star of David, all the deformations, how exactly, to which exactly amount of angstroms. And here we have this A star and B star reciprocal vectors of the distorted lattice. So that's well known, maybe from some previous experiments at room temperatures, or even, I mean, not even per distribution function experiments. And that's the fraction that is obtained from some fitting, I think, because they really know how to calculate, like here, that's the theoretically calculated per distribution function. So they know how to get this like function that represents correlations from whole collection of distances between atoms. And that's how they can plug different distances and get different results and compare, I mean, and do the fitting and deduce the distances between the local deformation. And these are comments about how exactly they did it and exactly the names of the symmetrical groups. So, but no discussion is present here. Okay, now we have finally the section of discussion, and it's also not actually an easy section. Let's see how much time I'm doing this. It will be 3 hours. But we have just discussion and also comments about magnetic ordering and the methods. Okay, I need really to speed up because I don't want to have 2 streams about it. So There are local distortions which evolves in temperatures. Polarons are seen at all phases because there are local distortions at all temperatures. Density wave can't predict these local distortions, and that's actually the repetition of the announcement that I did before. That's exactly why there are polarons. Why they're there actually? Yeah, okay, let's remind you that that's because of this fitting with local distortion. Okay, there is this figure 1D, which we haven't discussed much, and maybe this discussion will be here. So yeah, if we change temperature by 10 degrees, then we can see how much the pair distribution functions changed. And that's done for two temperatures. One is for metal temperature, another for income-measure density wave temperature. So the big difference is here for the low temperatures and for distances more than like 5 angstrom. Number of distorted sites and the extent of income-measure. Okay. I forgot to add this. Okay. That's what's written here. That yeah, like if you have more these changes, then it means that more stars of Davids appear. Yes. So there is no purely this symmetry. So in metallic phase there is polaronic gas. In income-measure density wave, again there are some local distortions. So this is a polaronic crystal. So now the recent income-measure density wave, as you know from the whole stream, and it becomes nearly commensurate. So there are several ideas. Maybe there is dynamics of charge density wave. Maybe some independent charges, or maybe some polarons appear. It's not explained here what is really meant by these ideas. We can only guess. But you can imagine that there are some theories that are not using words polarons. That's the best thing you can think about. Here it will be written that the conclusion is that the polaronic theory is the right one. The disadvantage of this discussion is that no formulas are present here, so they're not writing that, hey, that's exactly the formula that was used, and you can't use it because of our experiment. And like that's another formula that is used, and it definitely can be used. So we can only guess what is meant by these words: dynamic of charge density wave, independent charges, so on. Okay, but that's experimental article. If you know a proper way how to interpret this, then you can do it, unless they will come and tell you that you interpreted it wrongly. So we have this famous peak that no, I don't know actually which peak they mean here. When we speak about polarons, as was written before, we need to discuss this plot, because there is something that is explained only by local deformations. So maybe it's meant here by this peak in intensity, but it's not exactly written like this, so it's just my interpretation. And so it's not, it should not actually disappear if we go from metallic phase to incommensurate phase, and that's why there. Yeah, okay, so maybe that's what we see, that there is still this metallic peak, but if we have dynamics of charge density wave, then we will not have this peak. And that's how we prove that there are polarons And that's already a big achievement, because you might look at polaric theory and say it's absolutely impossible to prove that there are polarons, but okay, here we have local deformations, and we believe that that theory of polaron can derive some local deformations. But actually, okay, let me write this question to my list of questions. I haven't thought about this before, but it's a really good question. Is there a polar? So that's important point of the whole paper, that polaronic theory should predict it, but I haven't ever seen this theory, so maybe later I'll look again at this, and maybe it will be important connection of this paper to some theoretical work. Here is just the main argument of the existence of polarons, and the disadvantage of this argument is that we don't see exactly what is meant here. It's not written like disappearance of reflections, but which reflections in which plot we can only guess. Okay, and that's written here, that there is no such plot that is assumed. Okay, let's finish the discussion. So they exist, and they exist not always, just in little percentage, but still they are there, and that wasn't known before this article. But they're actually there only in 1T phase, and as you know, as I have explained, there are like several layers in the high temperature regime, and 1T phase, then 1H phase, so polarons only in 1T phase. Total, this configuration is called 6R phase. I don't know why, but that's well-known notation for the phases. And okay, they also have suggestions of the substrate, influence of substrate, that it should not destroy this effect. But again, they don't measure any substrate. That's just their ideas about it. Okay, and the final last paragraph of the discussion is the idea about magnetic ordering, and we need to look at this plot. So it's not really used much discussion, but the idea is again that we have some quantum spin liquid. So I mean, it could be that there is a quantum spin liquid, so maybe these local distortions can tell us something about the applicability of this theory or unapplicability. Okay, and the main idea will be during this whole 1 page, or actually 1.5 page, is that there are some signatures that are compatible with quantum spin liquid. Yeah, and that's above 50 Kelvin, that's below 50 Kelvin, but not between interlayer. So this spin liquid can be in one layer, but not between layers. That's, I guess, my conclusion. So let's try to read fast this and finish with this. So if we have local distortions, then there are magnetic groups that can be there also, and which will not contradict these local distortions. So it means that we need to put somehow spins, and these are the examples of how spins can be put it, and yeah, and these are the names of these magnetic subgroups. So not so much explanation is given about their names. And this gives us the constraint of magnetic moments. And also prime here means actually the time reversal symmetry, but it doesn't tell me something really informative. Yeah, so I mean, if you really use some advanced idea about the magnetic ordering, then you can see that actually here there is a time reversal symmetry, and here there is no time reversal symmetry. Okay, that's what I told already, and this is the images that you already see. Okay, so these spins later can be arranged in different way, and they could be correlated. And if they are correlated on a short range, then you can call this quantum spin liquid, and some people are very interested in this. So idea is that such distortions allow quantum spin liquid to occur. Also, it's not clear if we have one spin per polaron or not, because here we have a lot of electrons, but like 12 out of 13 electrons are used for bindings, and one electron is the electron that can hop, and this deformation can also change in space. So I thought that one spin corresponds, but it's not actually written like this here in the article, so it's just my guess. That only one spin should be per polaron. So they tried to expand this theory for another field of science about magnetism and spin liquids. But I don't think that there are some really informative conclusions about this. But definitely I'm not expert in this direction. So, okay, there are local symmetries at low temperatures and local distortions. Okay, so also what we know is that there are layers, as was drawn here. These are the layers, and spins can be also, okay, somehow they can point out of the plane and also be in the plane. So there is a spin relaxation, some spin relaxation somewhere there. It's not explained what is exactly spin relaxation, but this spin relaxation can be explained by the coupling between layers. Okay, also, I don't know why did they write it exactly here, but they write that, okay, the symmetry which appears here can be connected with disappearance of domain walls. I mean, it certainly comes from the disappearance of domain walls, and sounds like a very strange statement, because yes, domain walls disappear, the symmetries appear, but the connection is not established, so I don't know why they wrote this here. Okay, but okay, what is unusual, and it's not connected at all with the spins and magnetisms, that if we look at PDF, there are still some peaks which correspond to interactions between the Davis stars. So what turns out that there are still domain walls even in equilibrium, even in in equilibrium in commensurate density wave regime. So that's what's written here. Maybe it's connected with quantum spin liquid, because if there are domain walls, then okay, so definitely there is some idea of connection of domain walls and quantum spin liquid, because okay, maybe there is no dimerization of the layers, and if there are no dimerization, I don't know what to do. Yeah, it's unfortunately not very explained what is real this connection of the domain walls and quantum spin liquid. I mean, you see, that's the problem, that they write unclear statements, and now during the stream I need to explain something that was initially very poorly explained. Look, undimerized layers support intralayer quantum spin liquid. So, okay, the idea is that if there are domain walls, then layers do not couple much. If layers do not couple much, then spins are arranged more in one layer. And if so, then maybe they can realize quantum spin liquid. So it's a very vague and not informative idea, but that's the best thing I can extract from this sentence. Okay, that's a continuation of this unclear argument. Now if you do this shift to hidden state, so if you do this pulse and the domain wall appears in the Commander-Chernitsky wave, what then quantum spin liquid will be there where there are no domain walls. Okay, like that's kind of obvious. Okay, now we really know already that there are ordered polarons. So why we discuss it? Because local deformations can tell us something about spin polaronic effects. That's my extraction of this sentence. It's hard to extract something more useful than my little comment. And they finish all this article by idea that maybe in some other systems this ordering of polarons can be also there. So as I announced, this whole paragraph of the magnetic ordering is not very informative because it tells us just, yes, there are these possible directions of magnetic moments, then some ideas about quantum spin liquids, which are not very precise at all, and some repetition of the previous statements without like anything really informative. So I don't think that's a good idea to write like this. I mean, of course, I would not tell you what are the symmetrical groups by my own, so maybe it's informative, but it's like when I read it, I want to have some like conclusion and some explanation of why at all this is discussed, why these comments are given, and they're not here. And in scope of this discussion, what did we learn? We learned just extra comments and repetition of the statement that polarons are there, and I mean another argument. I mean another sketch of the argument, let's say. And that's the conclusion. So now there are methods which we will go through because that's the last one. And okay, oh my god, that's the last 3 pages, but I promise you I will do it way faster. I just don't want to leave it. So crystal growth and analysis. So the crystal grow, and there is a description how crystal of tantalum sulfide was grown, and they got finally the typical 1T phase because they did some energy X-ray spectroscopy. Okay, now how did they do pair distribution function measurements based on this device? And there are 2 experiments, which you can also remember from this plot, exp2 and exp1. They work in different temperature regimes. That's what is known, and that's why I mean, there is a question for me why we can't use experiment 1 in this temperature regime and vice versa, but that's advanced understanding of this experiment. There is information about the detector, about the X-ray beam. Of course, you might ask, like, why do we use X-rays, not light? Okay, let me read this question. Maybe the answer is that because it will not disturb material. Okay, but I'm not expert, so it's a good question. So this is the parameters of X-ray beam. Okay, that's how they control temperature. That's how much time it takes for them to do the measurement, and that's the temperature regimes for the first experiment, and also like information about cooling or warming, because as you remember here, for example, these are the data for cooling and warming. So if you really want to know which experiment used cooling or warming, then that's information about it. Okay, now there is the most important part of the methods for me as a theoretician, because that's the main part about data analysis, and not so much things are written here, but important citations are present. So there is a referenced measurement of reflectance, first of all. Using this reference measurement, they removed some bad pixels, so it's still about obtaining data. Then they used this XPDF suite and PDF get X3 to get these parameters. So it would take at least several days for me to figure out what is one of these programming packages these are used. And then another programming package PDF GUI is used for later analysis. They got a lot of data, and there are some uncertainties, by the way, also. So 1E, what happens at the plot 1E? Okay, so it's like connection of the calculation and the measurements. So one of the packages maybe was used for calculation, and that's again repetition of this plot, which we have discussed. That's the major influence of the tantum correlations. So I don't know why did they repeat it here, maybe because somewhere here it's written that they were calculating also maybe by this PDF analysis it means that yeah, carried out using modeling platform. So that's the code that was used for modeling. Okay, let me just write it a little bit more clear. Okay, that's information about this package. So that's how we model, that's how we get these basically results. So that's the processing of data, that's the modeling. Okay, now we have this distorted fraction that's hard to get, and if you really want to know, that's like 5 sentences that tell you. So they calculate the differences between PDFs. To get the fraction distorted sides. So they do some averaging else also. And okay, that's related more for the high temperatures, because at high temperatures you have 2 phases, and again you get no information about long range order, just about local distortions. And that's how, I mean, so don't say that something is really informative here, but I want to finish the stream as soon as possible already. So idea here, I mean, I don't see any informative here. Of course, we have these 2 fractions of PDFs, and you just tune their weights. That's how you get the distorted fraction. And by distorted fraction, they assume, I guess, not local distortions, but just existence of at all Star of David comparing to the fully symmetric case. Yeah, I don't know. Yeah. So they do some averaging, obviously. High temperatures. Yeah, so my conclusion is that nothing is informative here. If I'm wrong, then write it in the comment, but that's my conclusion. Okay, now we have this already symmetry of Star of Davids, these ones, and we have also local distortions. And yeah, of course, first of all, we fit with this symmetry of Stars of David. It has 19 parameters, and there is some discussion of it in supplemental information, which I haven't ever read and will maybe never read. I'm not interested in this, but you see that there are really a lot of parameters. See state. And of course, like at chart density wave, I mean, Commander chart density wave state here, it's a good fit, except that some local distortions, as we already know. And also, like, there are some distances at which all this fit makes sense. So that's also a comment about it. So again, nothing is really informative. I don't see something really informative about it. So I don't have explanation how local structure was obtained, but by local structure I mean local deformations. Maybe that's the most informative sentence, that there are these parameters that are fitted. And also, like, if you do fit, you do some averaging, so that's the discussion of what range they average. To do the fit. So it's like comparison of calculations and the experimental data, but again, I think that that's a very poorly explained section at all, this methods section. So I want to skip it as soon as possible, because it does not give any really informative information. Anyway, you would need to read cited papers and supplementary information to figure out this local structure. Okay, multi-phase treatment is about maybe high temperatures. Okay, so in nearly commercial density wave, as we well already know from this definition, sorry guys, that's the phase diagram. I mean, not phase diagram, but how phases look like this. So that's why it's obvious that purely polaronic symmetry is not very well explained in nearly commercial density wave. Then the main walls are there, as we know, and they take the weighted average, something like this, as far as I remember, for effect of the main walls, because the main walls are basically this undistorted phase. That's rather obvious. Is used. Okay. I have extra. I don't have a space here. I'm trying to remember what happened here. So several phases. Yes, that's what we know. Okay. Let me write like this. So yeah, like that's the typical idea of chart density on commercial chart density wave, that if we change the temperature, then phase from this will go to this. I mean, the distribution of electrons. So that's absolutely nearly useless part of methods, which do not give us something informative. Insert to 3C. Let's see it. Okay, but we have already discussed this plot in the article itself, so I think authors were really tired, like I am tired already after the stream, and didn't put much effort in the methods section. That's why I can't extract something really useful here. It's not like, oh, that's a good guidance of how to obtain these results. Still unclear. It's a big work to do this. extraction of data. And finally, we are reaching the last paragraph out of all this article: assignment and consideration of interlayer PDF peaks. So that sounds like the most important thing, that we need to like find out which peaks correspond to which distances. So for interlayer peaks, we have the symmetry. Multiple c-axis lattice. Okay, so there are some periodic peaks that gives us information about interlayer spacing. So there are layers, there are different distances between layers, and okay, yeah, that's maybe that explains something more that I didn't understand before. So it's about this plot. So this peak is wide. Why? Because layers are arranged like in slightly different distances one between another. That's why after averaging we get not a sharp peak, but a little bit smart peak. One special peak, a special contribution. Okay, and like if we look at the interaction between two what? Yeah, two layers apart, so maybe between layers, between two layers. So that's actually a nice observation, that this one is approximately 2 times bigger than this one. So that's why it's 2 layers apart, maybe. So that's the interaction of tantalum atoms between two peaks. Peak. Should be peak. So at high temperatures there are also what? Yeah, like different stacking, some fluctuations. That's why there are the peak broadens. Here's again when we change temperature. Yeah, so like there was bad stacking, then we maybe it was to read the sentence. Okay, so maybe the idea is that at high temperature the peak is, yeah, but actually what we see here, the peak is broad, smeared, but if we decrease temperature, the peak becomes sharpened. That's what corresponds to the better stacking at lower temperatures. And that's the paraphrasation of the previous sentence. So that's the extra comments about the interlaying these peaks basically between layers. So it does not tell us something like how to find out that that's exactly this peak, because maybe they know already a lot about the geometry, so they have already enough information to connect this geometry with the peaks. So maybe I missed something in methods, because actually I thought maybe not to read methods at all, like you're always lazy to read these methods. So rather technical, boring statements. But okay, I did it. I didn't find something really important and useful here. But okay, we have important citations for the codes that I used. So there is something, of course, informative. But okay, in general, it did not give some good extra insights. So that's the basically whole article that we went through today. We discussed all these plots, all our distribution functions, the results that are obtained from them, the change of pair distribution function. So maybe actually in terms of all their data, sorry for this fast scrolling. In terms of all their data, this is the most important plot because it shows all pair distribution functions at different temperatures. Then we do some subtractions, some extraction of parameters which are not written by any formula. What I can show you also is a collection of some questions and answers which I had during this preparation. So I was thinking about pair distribution function, the applications of the article, like what can we do? Well, we maybe can use some polaronic theory, and maybe we should not use some not polaronic theory. Maybe we can use it in some quantum spin liquid discussions, but that's the weakest part of the article, is that nothing is written about it. But you might, like, I expected it to be written because, I mean, if you do science, then you maybe know these answers, so why not to write these answers? Again, these are the U parameters that were shown in the whole beginning. So these are some ideas, I mean, ChatGPT's ideas of where you come from. But there are cited papers. So anyway, I would need to read the cited papers to really understand this connection. What I also tried to understand. There are also these ideas of the symmetrical vectors of the deformation, and that's also a derivation of them. I also thought about this, why exactly these numbers are there. And also there are important formulas for pair distribution function. These are steps that are done to get the final result. Yeah, there are deep ideas, discussion of which will be for another several hours, but this is general the framework that is assumed and never written explicitly in the article. That basically you measure intensity of the light, then you do some averaging, then you calculate some effective parameter, then you do this Fourier transform of this effective parameter, and you get the finally this PDF that was there throughout all of the stream with us. Another version of the same explanation. Maybe I need to delete something here, but when theories from ChatGPT, it's better to leave it like this and use it only if it's really needed. And right now, definitely it's not needed. And basically that's all. There is already next article. Yeah. Okay, that's an important. No, check. No, that's not important article about polarons. That's important article about observation of polarons, by the way. Maybe I will discuss it later in some stream. It has a lot of collections, a big collection of experimental confirmations of polarons. And basically that's the article that we have discussed, is the one that is providing one evidence of polarons using the pair distribution functions. So let's open it again, but did I close it? Yeah, I mean, I wanted to open it original. Where is it? Pair. Crystallization of polarons through charge and spin ordering in what is actually spin ordering transition is not nearly not explained at all. Maybe it's about the spins, so they also arrange somehow, but fortunately that's the part of a title which is not very connected to the text itself. So this article was just, as you know from the first minutes of the stream, it was just 7 pages, but it took me more than 3 hours to discuss all of this because there are really a lot of tiny details, tiny comments, and not much explanation. So some statements are at all ununderstandable, at least for me. And I'm sure that it's not worth of it discussing of this with ChatGPT, because If you really need, you need to read cited papers first of all, and only then it makes sense to think deeper about these results. And some statements are just unclear, so you can't do anything. Just not focus much on them and go to other statements. For example, this plot, the B plot in the first figure, nothing is explained about it. So yes, some parameters are there, somehow they're extracted, but as you can see, nothing is written in the methods, nothing is explained in the text. There is supplementary information, which maybe will give some light on this, but the best thing is to read just cited papers. Okay, so that's the stream for today. I did it. It was one of the hardest articles that I have ever read during this preparation for the streams. And the main complicated part of the article is that it uses pair distribution function method, and this method is not explained. So to understand this, I was thinking about some background a lot. And also this English and this quality of statements are not the ones that are enough for me to understand. But okay, in general, I got the idea and we did this discussion. So tomorrow there will be next stream when I will discuss way easier article about possible application of tantalum sulfide. And thank you for watching. Thank you, one viewer who is right now watching me. And thank you, one viewer, Unidited9, for the first ever comment throughout this whole history of the streams. I mean, I had some comments from my friends for the first like 3 or 4 streams, but this doesn't count. This is the first comment ever from anonymous viewer who found me in the internet. Okay, bye-bye. See you tomorrow, most likely.